I'm throwing at you, and a lot of sitting looking at me working math on a screen, but I hope this practice has helped you a bit. Okay, so here we go. The last thing today is we're going to be talking about geometric series. Now again, we know that when we see that word series, that means add them up. Add them up. So we're talking about geometric sequences where we're going to add up all the terms and see what they add up to. So geometric series is just the sum of a geometric sequence. Series means add them up. Okay, so say we had a geometric sequence that was 3, 6, 12, 24. I think you can probably see that those numbers have a common ratio. And the common ratio is 2. They're doubling. They're doubling each time. 3 to 6, 6 to 12, 12 to 24. So it's doubling each time, so that's definitely a geometric sequence because it's being multiplied by the same number each time. So the corresponding geometric series means add them all up. They all happen to be positive, so that makes it a little bit easier. And here's the formula we're going to use. So this is one I'd like you to add to your formula sheet, please. I'm going to add what a couple of those terms mean. I think you probably know a bunch of them already, just by the fact that we've used the same ones. There's actually 2 of these we're going to add to your formula sheet. Okay, so here come the big red boxes that we put around all our most important prized math possessions. And now we'll say what each of these are. S, of course, stands for sum. Sum of some number of terms, n terms. So that's actually well named. S stands for sum. A, of course, is our first term. Sorry, folks, my pen has seemed to die on me here. I might need to close down this file and start over again. So A is, of course, our first term. We also call that T1. Oh boy. There we go. And we already said our n is going to be our number of terms. And R, I'll point to the R down here, is going to be our common ratio. Now there's actually another formula I'm going to reveal right here. This is the one we use if our R value is a decimal number, a fraction, proper fraction. So if it's between -1 and 1, like say it was 0.5, 0.7, 4/5, or it could be a negative fraction, -0.3, -0.62, -2/3. Any of those, we'd use this flipped version of the formula. Now it turns out these formulas are actually pretty easy to use. So they look a little weird, but the fact that you've done the arithmetic one actually is longer and has more parts. The geometric one has less parts. And so solving problems with this one is actually a little bit quicker and often a little bit more streamlined than when we're dealing with the arithmetic series. Now we're going to look at 2 quick problems to finish off today. We've got 15 minutes, which will be plenty of time. I want to look first at an ancestor problem, number of ancestors, and then I want to point out a problem that's a good one that's from your textbook that is a fish population geometric problem. So I do want to move on from this page, but I just want to make sure you've had a chance to look at it. Again, this is in your textbook in section 7.6. This will be in the video, and this will be on the PDF that I post. So I am going to move on now. I hope you've had a chance to write it down on your cheat sheet. If you haven't, though, you'll have to do that after the fact. Okay, here we go. Let's first look at a pretty well, kind of a straightforward one. I want to know how many ancestors I've got if we go 10 generations back. If we go 10 generations back. So one generation back, talking about my parents, I've got 2 ancestors. If you go 2 generations back to our second term, each of my parents have parents, so then we're looking at 4 ancestors that I've got. And that's going to continue. And I think looking at this, you'll be able to see, okay, yeah, that's clearly a geometric series. That's a number that's going to keep doubling. It's starting at 2 and it's going to keep doubling. So if I want to write down what I know about this, I'll say, okay, my starting value, that's my first set of ancestors, that's 2. My common ratio is also 2, keeps doubling. 2 means it's doubling each time. And of course my end value, I'm going 10 generations back. So I want to know what it'll be if I go 10 generations back. So let's get out our formula for calculating sums of a geometric series. I say, okay, the sum of a certain number of terms is going to be your first term, times common ratio to the power n minus 1 over common ratio minus 1. And let's sub in what we got. For 10 generations back, our n value will be 10. I'm starting with 2 ancestors. That's my first term. I'm doubling each time. And I'm going 10 generations back. So I'm just going to sub in my values for this whole equation. Now, convenient thing is if we look on the denominator on the bottom, 2 minus 1 just equals 1. Dividing anything by 1 doesn't change it. So I can actually just write it like this. Because dividing by 1 wouldn't change it. Now we've got to figure out what 2 to the 10 is. So plug that into your calculator. Make sure you can do that. It's going to be 1024. And this will give you an idea why those genealogy charts get really busy really fast. So I'll have 2,046 ancestors if I go back 10 generations. So that would be my, let me see if I can figure this out. I got my parents, that's term 1. Then I got my grandparents, that's term 2. And then great-grandparents is term 3. Great-great-grandparents, great-great-great-grandparents, great-great-great-great-grandparents, and then add 4 more. So that would be 8 greats on there. That would be the last generation. But it adds them all up. It includes my parents in that too. So 2,046 ancestors, distinct people if I go back 10 generations. Now there is a question here. If I put a much bigger number, maybe not 10 generations, maybe I want to go back like, I don't know, let's say 40 generations. Certainly humans have been around a lot longer than that. So if I actually want to figure that number out and I put in 40 generations, you're going to find that pretty soon, because you're dealing with exponents, you get to this, yeah, that's right, Sam. So, but actually, Sam, this doesn't matter for the amount of kids you have, because each individual kid can only have those two genetic ancestors. So, so that is a factor in population size, but it wouldn't actually factor into this because you can only have those two distinct ancestors. Great point though, thank you. But you might get this huge number, this massive number when you go back more and more and more generations, and you might get to the point where the number is so big that you're like, that many people have not lived in the history of humans. So how does that make sense? Well, because it turns out if you go back far enough, you don't have distinct ancestor lines. It turns out one person will actually be an ancestor to multiple people in your ancestor tree. So those lines will converge, right? Those lines will eventually converge, and you'll have one person actually taking the role of two ancestors because they have two lines that come from them that then converge many, many, many generations later. So it turns out that you can end up, if you go back far enough, with numbers that are bigger than the number of people that have existed, and that's why. So this one actually isn't too bad. I think you can probably see that this one is not nearly as mucky as the arithmetic series, adding them up. Here's another population type one. This is one from your textbook. So this is fish hatchery, and I'm just going to kind of take you through this. I don't actually want you to do this because I don't think we have time today, but I just want to show you this as an example. This is on page 456 of your textbook. At a fish hatchery, fish hatch at different times even though the eggs were all fertilized at the same time. The number of fish that hatched on each of the first 4 days of fertilization was 2, 10, 50, and 250. So those are the amount that hatched on the first 4 days. If the pattern continues, calculate the total number of fish hatched during the first 10 days. Now there's an important thing here. It says if the pattern continues, and it can't continue indefinitely. It will taper off at some point. But it probably will look like this for the first few days. That gets into mathematical modeling that we've talked about. At what point does this stop being a geometric sequence, even though it might start out as one? So here's what your textbook says about it. Your R value is 5 because it's being multiplied by 5 each time. Your starting value is 2, and your number of days is 10. Plug that into our equation, and we end up with 4,882,812 fish hatched during the first 10 days. Now that's probably not accurate because that number probably doesn't keep going up by times 5 each day. It probably starts to taper off significantly at a certain point. So if you were using math to try and figure this out, you wouldn't be correct to assume that it would keep being multiplied by 5 again and again and again and again. That wouldn't make sense in this case. That number is going to start to taper off at a certain point. But if it continued, that's how many we'd have. We'd have almost 5 million fish hatched. Okay, so I wanted to leave you that. I know that's a ton of stuff today. I've piled on a lot. Tomorrow we're just doing a review. No new stuff, just some challenging problems that we're going to tackle together, some review of our basic and most key concepts, and some practice. Tonight, here's stuff I'd like you to work on in order to practice this idea of geometric sequences. You'll notice it's a bit faster and it's a bit quicker and in some ways easier than arithmetic sequences. So do your best. So here's the stuff I'd like you to work on tonight. This is also on EDSB, of course. And if there's any of these you'd like me to take up, send them my way. If the solution set doesn't satisfy you, which it often won't. And the questions people asked about the homework from last night, I'm going to go right now and I'm going to make a video about that. And I'm going to post that to today's lesson as well as a video that you can watch. Okay? So thanks for hanging in there with me today. You folks are awesome. I love doing math with you. This was a lot of stuff, and I appreciate that we're pushing through so we can do that. Tomorrow's a review day. Thursday will be T-Day, test day. So if you find you're feeling shaky on some of these concepts, or you're unsure, having difficulty, and you want some extra support, now's the time to get on that. You should be letting me know. Either stick around today after class and I can give you some extra help for a while, or stick around after class tomorrow and get some extra help. I'm happy to give you a hand to anybody. All you have to do is let me know, or stick around after class and let me know, and I'll be happy to give you some extra help. It's 11:55. It's almost that time. So unless you've got questions, I'll ask you to please unmute, to say, have a great rest of the day, wish your classmates well, and then you can head on your way. Great. Amy, let's just give everybody a chance to head out if they're done, and then I'm happy to take that up. Thanks, everybody. Have an awesome rest of the day.